Okay, we have seen 3 types of detectors, and the difference was where we put them, at the router, in the hosts, or a script that scans all the logs. In this section, we will now look at how you measure how good detectors are. So in order to measure whether a detector is good or bad, we have to think about 2 types of errors. There are 2 ways in which detectors can go wrong. One is a false positive. This means that the detector said, yes, there's an attack, but there actually wasn't one. The real answer was no. Detector said yes. They got it wrong. That's called a false positive. The other one is called a false negative. That would be the case where there is an attack. So the answer is yes, there's an attack, but the detector fails to catch it and says no. The answer was yes. The detector said no. We call that a false negative. These are the 2 types of mistakes that a detector can make. And we usually try to measure accuracy in terms of how often these happen. So for the false positive rate, you collect all of the non-attacks, and you count how many were alerted as attacks. So if there are 100 non-attacks and 5 of them were accidentally alerted to be attacks, then the false positive rate is 5%. That's only out of the non-attacks, and you count how many were incorrectly flagged. For the false negative rate, you count up all the attacks. Maybe there are 5 attacks, and the detector missed 1 of them, so the false negative rate is 20%. There were 5 attacks, you missed 1, so 20% of the time you missed attacks. That's how you would measure accuracy. You need both of these terms to describe how good the detector is. So if we have these 2 measurements, one question is whether you can build a detector that's perfect. What is the absolute best you can do? Could we get the false positive rate all the way down to 0? In other words, for every single non-attack, none of them get accidentally flagged as attacks. Could this be done? You can try and predict if the answer is yes or no. Can we build the detector that never gets the false positives wrong? For every time there's not an attack, the detector always says no. Turns out this is possible, and it's actually something I can fit on 1 slide. So here it is. That's it. This is the detector that has a 0% false positive rate. It takes the input, it throws it away, and it says no, it's not an attack. So we're not even looking at the input. We just say no every single time. Now, if we plug this into our definition from earlier, there are 100 attacks or 100 non-attacks. This detector just says no to all 100 of them. So you get false positive rate 0%. We did it. We built a perfect detector. Now, what about a detector with false negative rate of 0%? Maybe you see where this is going. Can we build a detector that never misses an attack? If there's an attack, we always catch it, and we always say yes. Once again, it's possible. We can do it in 1 line of code, and here it is. We take the input, we throw it away, and we say yes, it's an attack. Once again, if there's an attack, we're not going to miss it. This is going to work 100% of the time, because it detects everything. It just says yes to every single input, so it won't miss any attacks. So these 2 are pretty silly examples. You're probably not going to use a detector like this in your system because it doesn't even look at the input. It just always says yes or always says no. But what we're trying to show here is that there are trade-offs. So to build a good detector, you want to balance false positives and false negatives. You can get 0% false positive rate or 0% false negative rate, but by doing so, you usually sacrifice the other. So the goal is not to get one of them to 0%, but to find a good balance between them. Now, what is the right balance? That depends on your system and your threat model. So for example, how often do attacks occur? That can affect the quality of your detector and which of these 2 you want to optimize. Another big question that affects how good a detector is for your system is how much the false positive costs and how much the false negative costs. So sometimes it's better to make a mistake in one direction than make a mistake in the other direction. One classic example of this is the fire alarm. So a fire alarm is a detector. It says yes or no to whether there's a fire, and sometimes it gets it wrong. So a false positive would be a case where the fire alarm goes off. So we said yes, but there wasn't a fire. A false negative would be the case where there is a fire, but the alarm doesn't go off. The answer was yes, we said no. So which is better? In the fire alarm case, do we want to minimize false positive at the expense of a higher false negative rate? Or do we want to minimize false negatives at a cost of false positives? Which one is worse? That's something we can use in our analysis. So let's reason through it. If there's a false positive, the alarm goes off, but there was no fire. Well, in that case, you have to step outside in your pajamas at night. The fire department has to come and inspect the building. And then there's no fire, everything's clear, and you can go back to work. So you've just wasted 10 minutes of everybody's time. That's the cost of a false positive. You wasted everyone's time, and you had to go outside and wait. And that's basically it. What about the cost of a false negative, where there is a fire, but the alarm doesn't go off? You don't have a building anymore. It's gone. It's burned down. That, to me, seems a lot worse than a false positive. I would much rather waste 10 minutes than not have a building anymore. So here's a case where the false negative is much more expensive. So if I'm given a choice of a bunch of detectors for my fire alarm, I would want the one with the lowest false negative rate, even if it does have a bunch of false positives and goes off all the time. Here's a case where I might prioritize the false negative over the false positive. So that's a type of cost analysis you would have to do for your system.